Okay. Any other questions? Okay. All right. So last week was about divide and conquer. Just a whole week about divide and conquer. And this week and sort of really until the midterm, we're going to transition to graph algorithms. In some ways, this will structurally be similar to the first segment of the course. We sort of did some dynamic programming and implicitly a lot of emphasis on induction, and then we switched over to like DAG and shortest path and lots of graph algorithms, and then a lot more problems became related to changing the input, these graph reductions and stuff like that. It seems like the second segment is shaping up similarly. Last week's divide and conquer was sort of again about induction, but in a different sense, more emphasis on faster running times. And now we're switching over into some kind of pretty fun graph algorithms. So today we'll be spanning flows, and then Thursday spanning trees. And then Thursday we'll start what's called max flow and network flows and the edge disjoint path problem. So I think it'll be similar to the way that we did several lectures about, say, shortest paths and stuff like that. Okay, so, all right, spanning trees. It's like the nicest graph algorithm subject. Everything works out really nicely. Okay, but here's sort of I think a historically accurate representative problem from, I guess, the late 1800s. When they're installing electricity into towns for the first time. And at some level, you want to connect all the houses with electric wire, copper wire, or whatever. What I've drawn is sort of places where you could put wire. Okay, and you want to make a kind of a connected subgraph. So you want to choose some wires so that all the houses are connected to each other. Okay. Just one path from house to house is fine. We're not worried about like redundancy or something like that here. That's a different class of problems, or rather an extended class of problems. And okay, so let's say that the amount of wire used to connect two houses is roughly proportional to the length drawn on the screen. And suppose we wanted to ultimately connect all the houses with the minimum total amount of wire. Okay. So, I can only just try to guess, but I think that somehow the shorter wires seem naturally very appealing if the goal is to minimize the total amount of wire. So at least we can maybe follow that path and see how it looks. So I'm roughly just highlighting what appears to me to be the shortest edges in the picture. Okay. But in this way, we've put some copper wires and connected all the houses to each other. Maybe one of those houses represents an electric plant or something. Okay, so that's roughly the problem. This kind of thing really does come up. Of course, houses there's not that many houses in the world, but you can imagine connectivity being very important on a CPU chip, right, which has just billions of components in a very tight space, okay, and stuff like that. So we want to figure out how to do this algorithmically. We want to be able to do it fast, since real networks now are much bigger than 5 hand-drawn houses. Okay, but just some basic observations before we really launch into our study. Okay. One, as I was just doing it by hand, I don't really know if I had the best solution, But one thing that was sort of clear is that at some level, there is no point in having any cycles among the wires that I pick. Okay, so a cycle is somewhat redundant. One of those edges doesn't really introduce any new connections. Okay, so just, we can already kind of see that sort of, there's no need to have cycles. They're sort of, redundant. Okay. At least, we don't know much about the problem in any formal detail, but at this stage, I think it's pretty clear that, we're still, all things being equal, and maybe there's a lot packed into all things being equal, we do, at some level, prefer the shorter edges. Okay. So, from like a local point of view, I can take our solution here, and, I could consider replacing, say, that edge, very small edge, with this edge. Right? And now I'll reconnect my network. But at least locally speaking, there's really no incentive to do this. I maintain connectivity, but I'm just using more wire by replacing a shorter one with a bigger one. So there's some bias towards shorter edges. Okay? But then one thing that maybe is worth noting is that if again I look at this edge here, which again does not feel very appealing at the moment because it's bigger than any single replacement, okay? But it is in some sense shorter than sort of the path in our network instead. Okay? So it does seem like it's possible that omitted edges are shorter than kind of the alternative path in our solution. Okay, so it's sort of like not 100% obvious that we shouldn't use that edge. Is all that's suggesting. Okay. All right. Okay, so let me start off defining these things a little bit more formally. Okay, so you kind of guys know these definitions. So everything today is going to be in an undirected graph. Okay, and I'm just worried about connectivity in undirected graph. So a connected component just means there's edges from one to the other. I don't have to worry about direction. There's no notion of strongly connected components. In a way, every connected component is automatically strongly connected because you can always go in both directions along an edge. Okay. A circuit, we know from things like traveling salesman, is a walk that starts and ends at the same vertex. A forest is any set of edges that has no circuit, which is the same as having no cycle. Cycle, the only distinction being kind of there's no repeats except for obviously where it starts and ends. And a tree is a forest, so there's no cycles, there's no kind of redundancy as far as connectivity goes, but it's otherwise one component. Everything is connected. Okay. I think you guys have all seen this before. Okay. Here's some new definitions though. Fancy words to capture our notion of connectivity. So the key word here is spanning. So imagine I have a set of edges S, okay, and another edge E. I say that S spans E if S already connects the endpoints of E. Okay, so a set of edges spans another edge E if sort of E doesn't really introduce any novel connections because the endpoints are already connected in S. Okay. introduce some mathematical notation. I'll define the span of S to be the set of edges that are already spanned by S. Yeah, okay. All right, so at some level, with respect to my connectivity problem, I've already laid some wires, and that makes some other wires kind of redundant. They don't introduce new connectivity because the endpoints are already connected. Okay, so that's the word we'll use to capture that. And finally, I say S is spanning without qualification, just altogether spanning, if it spans every edge in the graph. Okay. All right. We'll use these words so much it'll soon become second nature. Okay, so with this vocabulary, we're going to look at two problems. Okay, I thought I had a nicer version. Okay, I do. One is to compute a forest. Let me go to the one with pictures. Okay. One is to compute a forest, so no cycles, with as many edges as possible. The other is to compute a set of edges that spans the whole graph with as few edges as possible. Okay. And then once we deal with this cardinality version, number of edges, we'll deal with weighted versions, where I now want to minimize the total weight in my spanning set of edges, or I want to maximize the total weight in my forest. Okay. Now, I want to make... Okay, so the problem I posed to you, this ancient problem of connecting a town with electrical wires, that probably sounds a little bit more like problem 2. I want to make sure that sort of all the potential places to set wire, all the yellow lines, was spanned by the wires I took. I probably presented to you the weighted version of the problem. You know, connecting the whole town was equivalent to sort of spanning all those yellow edges. Okay. On the other hand, one of our observations that came out of it was that if I'm trying to minimize, it seemed like there was no reason to have any cycles. So there was some flavor of forests and trees showing up in that problem. We'll clarify this. Okay. Now, I want to suggest that we're going to talk a lot about how these two problems are maybe two sides of the same coin. Okay. And very kind of abstractly speaking, the first type of problem is sometimes called a packing problem, in the sense that I'm trying to take as many edges as possible, but I can't have any cycles, right? So out of every cycle with 10 edges, I can only take at most 9 of them. And that holds for every cycle out there. Okay? So these problems where I'm trying to take as much of something as possible, subject to a bunch of sort of maximum capacity constraint. You can't take too many of this, you can't take too many of that. That's sometimes called a packing problem. Okay? And then the opposite this packing covering framework will be more useful as we build on the theme in upcoming lectures. The opposite is things like is covering problems. Okay? So in the minimum spanning set problem, I want to take the fewest number of edges, but making sure that all the edges are spanned. So I have to take enough edges to kind of make sure that everyone is connected. Okay? So we can think of sort of spanning an edge as sort of like covering an edge. And we find ourselves sort of wanting to take as few of something as possible, subject to a bunch of minimum requirements. You have to take enough edges to span this edge. You have to take enough edges to span that edge. You have to take enough edges to connect the whole town. Okay. So in that sense, it's a covering problem. Okay. All right. And we're going to get to understand these problems really well, but I think one thing to keep an eye out for is how we're going to understand both of these problems simultaneously And together that's going to paint a really compact and clear picture of what's going on. Okay, one idea is sort of each problem taken alone tells you less than both problems considered together. Okay, so here then is a very strong lemma, although it appears simple, where you immediately see both problems come into play at once. Okay? So let's, for simplicity's sake, that G is a connected graph. Okay. So let me draw some vertices. And I'm looking at two sets of edges. One is some kind of forest. So it's a set of edges that has no cycles. Okay, maybe that's a forest. Okay. And the other set of edges is a spanning set of edges. So maybe it's fully connected and there's even some redundancy. Here, green is spanning. Okay. And then from this picture, maybe it's not too surprising, but it says that the number of edges in any forest is at most the number of edges in any spanning set of edges. In particular, for connected graphs, there is at most n-1 edges in a forest, and there are at least n-1 edges in any spanning set. And what's kind of interesting is immediately we've now related the two problems by realizing that the size of any forest is bounded above by the size of any spanning set. Okay, so they kind of can't cross over, they limit one another. Okay, so here's sort of one approach. Okay, let me put this aside. All right. So we're going to do counting arguments based on, simple arguments based on the number of connected components. As we know, there's at most n connected components always. That's one for every vertex, and there's at least one connected component, if everything's connected. So, okay. All right, so imagine I have, initially, we have a bunch of vertices, and let's say that we have some forest in mind. Okay, so let me draw it in dashed edges. Okay, there's, I guess, a tree. Okay, but let's pretend that now let's imagine starting with an empty graph and adding the edges one by one until all the edges from the forest are added. Okay, so think of these dashed edges as edges that haven't been added yet, but we eventually will add. So initially there's n is equal to, I guess, oops. So initially n is equal to 8. Okay. And the number of connected components in the empty graph, ignoring all the dashed edges, is 8. Every vertex is its own isolated component. Okay. Now, as I add one edge at a time from the forest, I'm claiming that the number of connected components always goes down by exactly 1. Okay, so here I've just added 1, and now the red is sort of our graph. There are 7 connected components. 2 of them were grouped together, 2 of the vertices. Okay, so 6 connected components, 5 connected components. Okay. Something that wouldn't introduce a new connected component is if I did something like this. Right? If I added an edge between 2 vertices that were already connected, that wouldn't decrease the number of connected components because it just adds a redundant connection. But that can't happen for our forest because whenever that happens, there's a cycle, and our forest has no cycles. There's no redundancy connection-wise in our forest. So every time I add one more edge from a forest, because I can't create any cycles, I'm promised as connecting two different connected components, the number of components goes down by 1. I start with n connected components. At the end, there's at least 1. And every edge from my forest decreased by 1. So I could have only added at most n minus 1 edges from my forest. Okay. All right. Okay, so nothing too complicated. We'll do a similar thing for spanning set. It'll sort of be the opposite argument. There's going to be a lot of opposites between forests and spanning sets. So let me set up some vertices again. Okay, it's connected graph, so a spanning set will be a connected subgraph. So I'll add some redundancy, right? Okay, so here is, let me do the dash thing again. No. Okay. All right, so imagine the green as a set of edges that spans the whole graph. Okay. And now imagine, I guess I didn't have to do the dashes. Imagine that I delete edges one at a time. And we'll count the number of connected components. Okay. So initially n is equal to 8. 8. Okay, and the number of connected components is 1 with respect to the green edges. So the green edges are all there to start. Okay. And what I'm going to do is delete green edges and watch the number of connected components possibly increase as we start to split things apart. Okay. So for example, if I delete this edge, then we have 1 connected component here. Now my number of connected components is 2. Okay. If I delete this edge, I have actually not increased the number of connected components. Right? It's still the same. But now, okay, we're up to 3. Still the same number of connected components. Now we're up to 4 connected components. Still the same number of connected components. Up to 5 connected components. 6, 7, and 8. Okay. All right, so as I delete all the edges, I'll start with a connected graph as 1 connected component. And I'll move on to I'll eventually end up with nothing, and I'll have n connected components. Okay. But the key point is that every time I deleted 1 edge, the number of connected components may or may not go up, but it goes up by at most 1. I don't introduce, the number of connected components never went up by 2 as I deleted an edge. So each edge only gets me 1 point at most. Okay. So to go from 1 to n, I need n minus 1 points. So there must have been at least n minus 1 edges in my spanning set. It had to be at least n minus 1 green edges just to go from 1 to n. Okay. All right, so that is, so that's our statement, is that any forest has at most n minus 1 edges, and any spanning set has at least n minus 1 edges in a connected graph. Okay, so the natural generalization is to consider disconnected graphs, right? Maybe we basically have 2 copies of my earlier example. Okay, so the green are spanning edges, the red form forests. Okay. And let's let, for some reason the convention is kappa, which might as well be k, but let's let kappa denote the number of connected components. So in this silly picture, kappa is equal to 2. In a connected graph, kappa is equal to 1. Okay? And the claim is that any forest in my disconnected graph has at most n minus kappa edges, and any spanning set has at least n minus kappa edges. Okay? All right, so this proof is, okay, maybe I'll open it up. How can I leverage our previous lemma and extend it to this disconnected case? At some level, I'm generalizing from kappa equal to 1 to general kappa that might be bigger than 1. Yeah.
Could you repeat the question?
Yeah, okay. So previously we showed that if G was a connected graph, then I have these limits on how big a forest can be and how small a spanning set of edges can be. I want to take this and extend the idea to graphs that might not be connected to begin with. So it's a forest in a connected graph, or a forest in a disconnected graph. That means it's definitely not a tree. And a spanning set in a disconnected graph. Yeah.
Couldn't you treat each strongly connected component as a vertex in itself, and then apply the original theorem or the original lemma to that?
Yeah, and I think by vertex by itself, I think you mean a graph by itself. Okay, so we can just treat each component as sort of a separate graph onto itself. Sort of have nothing to do with each other. Okay? So, maybe over here there's n1 vertices, and over here there's n2 vertices. Okay? So if I look at the forest restricted to one graph, it's going to have at most n1 minus 1 edges. And a spanning set will have at least n1 minus 1 edges. Because that's by itself a connected graph. So for each component by itself, I'll have f is less than or equal to the number of vertices minus 1. And if I add that up over all kappa components, I'll get n minus kappa. Because each vertex will only get counted once. Same thing on the spanning side. I know that each of those components taken alone, it has 10 vertices. My spanning set has at least 9 edges. It has 20 vertices, there's at least 19 edges. So I add that up, and I conclude, each time I subtract 1 for every component, and overall I conclude the spanning set has at least n minus kappa edges. Okay, so on one hand, we're just adding up n minus 1, where n's correspond to the individual components of a disconnected graph. Okay. All right, so what's next? Okay. All right, so this is all set up for the following claim, which will bring some unity to all this counting. Okay, so what we've sort of shown to this point is some bounds on how big a forest can be and how small a spanning set could be, which in particular showed that forests are smaller than spanning sets, no matter the forest, no matter the spanning set. But we are interested sort of in maximum size forests and minimum size spanning sets. Okay, so we haven't said anything about these extreme points, and that's what we're going to address now. So F continues to be a forest, S continues to be a spanning set. I know that F is less than or equal to S. Now, the first claim is that if F is a maximal forest, so I can't add any more edges to it. It's locally optimal. I can't add one more. Okay? then it's also going to be a maximum size forest. And in fact, it's even stronger. We're going to actually directly prove that it's spanning. So if you have a forest and you've added as many edges as possible, you can't add any more, then we'll actually argue that it's a spanning set. Okay. But knowing that it's a spanning set, and that any spanning set is bigger than any forest, then tells you that this maximal forest is the maximum possible size because it hit an upper bound. And then we're going to have the same kind of symmetric claim for spanning sets. Okay, recall that our goal is to find the minimum number of edges that spans the whole graph. And this is saying, okay, let's say that S is minimal. I can't remove any more edges. I don't know if it's minimum, but I know that I can't remove a single edge without destroying this spanning property. The claim is that when that's the case, your spanning set is a forest. There's no cycles. And now, knowing that it's a forest, and now forests are always smaller than spanning sets, you actually know it's the smallest possible spanning set. Maybe not uniquely the smallest, but it's hit the lower bound. Because it is the size of a forest, namely itself. So, we walk away with the conclusion that maximal forests are maximum forests. And it turns out you can just add edges until you're done, and then that actually solves the problem. And also minimal spanning sets are minimum spanning sets. You can just delete edges, and then when you can't, you're done. Okay? But I think what's going to be most interesting about the way we argue is the way we're using kind of this forest and spanning sets to play off of each other. We need the notion of spanning sets to figure out that our forest is optimum. We need the notion of spanning sets, forest, to figure out that our spanning set is optimum. It's going to make it much easier to be studying sort of two opposite problems at the same time because they meet in the middle and certify each other to be optimum solutions. Well, Thursday's problem will also have this feature. There's going to be sort of a packing version and a covering version. And only by understanding both problems at the same time we'll be able to understand how to solve both of them. Okay, so let's prove this from the forest perspective first. So let's say that F is some kind of forest. Okay, and we claim it's maximal. So, or we know that it's maximal. Okay, so I can't add any more edges to F. Okay, and the claim is that it's spanning. It spans every edge, meaning it already connects the endpoints of any other edge out there. Okay. So we'll prove this. Okay, by contradiction, suppose F is not spanning. So F does not span some edge E. Okay. So, I don't know, there's some edge E. And so we know that it can't look like this because this edge is spanned by F. The endpoints are already connected. So it must go across components, something like this. Okay. Now if there's an edge that's not spanned by F, that also means that sort of adding it to F doesn't introduce any cycles, right? Because if somehow if this did introduce a cycle, that means magically we should be able to walk around and get all the way to the other endpoint, but that means it's spanned. Okay, so that's it. We're just roughly following the definitions of span and forest. Okay? So if F is maximal, or if F doesn't span an edge E, I can always add it to F. The contrapositive is that if F, you can't add any more edges to it, it must be spanning. Okay. So that's one side. Okay. and now the other half is about minimal spanning sets, and okay, so and whether they are minimum and whether they are forests. Okay, so let's say that this is my spanning set of edges or something, not drawn to be minimal. Okay. All right, so what's the best way? Okay. So let's say that F is the set S, which we claim is minimal, is not a forest. Okay, so let me draw it so that it's not a forest. Okay. If it's not a forest, then it contains a cycle, by definition. Here's the cycle. Okay. And then, of course, if I delete any one edge from the cycle, the connectivity is repaired by the other side of the cycle. So I don't lose anything from the spanning set. I don't lose any connectivity. Any endpoints that were previously connected remain connected because I can always replace my deleted edge with that walk around the other side of the cycle. Okay, so if this set was not a forest, then I would be able to delete one more edge and make it smaller. But then it couldn't have been minimal. Okay, so we conclude that any minimal spanning set must have been a forest. If it wasn't a forest, there's a cycle with some redundancy we could have deleted. Okay, so that's that fully resolves the first questions, which was how do I take a maximum size forest? It turns out maximal is good enough. And how do I take a minimum size spanning set? How do I connect the town? It turns out minimal is good enough. Okay. So that means kind of straightforward algorithms like repeatedly adding edges to a forest until I can't add any more gives you the optimum solution. Very simple algorithms, but we have to do some special care to argue that it's correct. And then the other simple algorithm for spanning set is I start with all the edges, and I repeatedly delete edges as long as it remains a spanning set. Until I can't anymore, it's minimal, and now it's minimum. Yeah?
Well, what's the distinction between minimal and minimum?
Okay, good. So we're talking about an issue of local versus global, sort of locally optimal versus globally optimal. So in the sense that in the original problem, I really am interested in all possible ways to, say, build a forest, the one with the maximum number of edges. Okay, that sort of represents the global one. Okay, and I'm comparing it to a locally optimal solution where sort of willy-nilly I just keep adding edges in any order until I can't add any more edges while retaining a forest. So at the end of that kind of very straightforward and not very calculating algorithm, I know that I can't add any more edges. So in some sense it's locally optimal. I can't add and I can't do a small change and get a better solution. And what I want to justify is that reaching a local optima, which again is algorithmically simple, can be justified, and we can argue that it really solves the entire problem. It's not just that it can't be improved in an easy way. So by contrast, I think almost every problem we've ever looked at, this doesn't hold true. We had to do some more aggressive global searching, like in dynamic programming, where we're roughly going over many options. Okay, so you can call this a greedy algorithm insofar as it really is very short-sighted. But this time it actually works. I think for all our problems, greedy algorithms never seem to work up to this point. But to get away with it, we had to spend a fair amount of time thinking about the problem, looking at some definitions, and only by setting up sort of some mathematical facts, then we could justify this very simple algorithm. Yeah, so this is very, spanning trees are actually very unique for a very good reason. In the fact that locally optimal is equal to globally optimum. This is a big topic in combinatorial optimization, where they try to sort of take spanning trees and generalize it and understand what are the class of problems where simple greedy algorithms works. Okay, there's a fancy word called matroids. But at some level, there are objects that act and behave like spanning trees like this. They all have this nice duality, kind of packing version, covering version, very clean theory. Yeah, some of just generalizing everything we discussed. Another example is independent sets of vectors. If you're trying to take as many vectors as possible, subject to being linearly independent, as you know, you can only take D vectors, where D is a dimension of the space. It's always the same size. That's the same as sort of spanning trees, right? There's a limit of n minus 1, a clean number. Okay. Anyway, so that's another topic. Okay, but it's in some sense a discrete analog to, when we do convex analysis, right? We know that when you get to the bottom, the locally optimum, and you can check the gradient, you've solved the problem. And this is very similar. This is sort of a discrete analog of convexity. Okay. And if you did convex analysis, you would look at the dual, which is, it doesn't matter. Okay. So, so there is something going on under the surface and connections to other problems that behave very nicely and have similar local optima meets global optima type of characteristics. Of course, we're not emphasizing that here, but I've set it up so that when the time comes, that connection can be made. Okay? All right, so much for the unweighted versions. Really? Sorry. Okay, let's look at the weighted versions of the problem. Okay, so now the edges have weights, and I want to get the maximum weight forest or the minimum weight set of spanning edges. Okay. Okay. Let me make one more. Okay. I'm assuming positive weights for all these problems. Okay. Now, one point I want to make is that there's going to be a little bit of flipping the bits here, which is annoying, but it is what it is. Okay. So, I want to get a maximum weight forest, okay, or a minimum weight spanning set. And I do know that in general, for forests, I might as well take as many edges as possible, assuming the edges are weighted. Okay? So I already know that whatever the maximum weight forest is, it's going to be spanning, because I might as well add more edges. Okay. So it will be a maximum cardinality set as well. And I know that whatever's the minimum weight spanning set, it'll be a forest. Oh, did I get backwards? Whatever's the minimum weight spanning set, I want as few edges as possible, of course keeping track of weights, but there's no point in having any cycles, as we've gone over. So whatever the minimum is, it'll be a forest. Okay, so what we're really looking for is a maximum weight spanning forest, as well as a minimum weight spanning forest in either problem. Okay. I say this because what we're going to reframe this problem as, which is going to flip a little bit upside down. What we really establish is that maximal cardinality true forest will give you spanning forest, and vice versa. But I think you'll find that in all the literature, we focus on minimum weight spanning trees. Okay, so to make things simple, we're going to assume that the graph is connected. Okay. So there's only one connected component in the graph. And we're going to assume the weights are positive. And I want to get a tree, so it has to have n minus 1 edges, okay, of minimum total weight. Okay, so I want to get a spanning tree of minimum total weight, which is a little bit annoying because we talked about getting forests of maximum size, and now I'm doing minimum weight spanning trees. I'm going to make one more assumption to make our life easier, which in hindsight you don't have to worry too much. I'm going to assume that all the weights are distinct. Okay. So I want to get the minimum weight spanning tree subject to the graph being connected and having distinct weights. Okay. All right. Are we doing? Okay, we're doing minimum. Okay. You'll find also afterwards that you can just as well look at maximum weight spanning tree problems, and you can do the same thing, or you can flip the weights upside, negate the weights. Okay. But the convention is to, in most textbooks, is to study minimum weight spanning trees, so that's what I'm doing here. Okay. All right, so we're going to present 3 different algorithms, God willing. But I want to try to argue that they're roughly all the same algorithm in the sense that we're going to see that they're all correct for basically the same reason. Okay, they'll have slightly different running time properties, but their correctness will really come from the same place. Okay. And it's all going to be centered around this notion of good edges. Okay. I'm going to say that an edge is good, an edge E is good, is if every time I have another set F of edges that spans E, so it connects the endpoints of E, okay, there's some edge of weight bigger than the weight of E. Okay. So at some level, it's sort of like for every other sort of alternative way to connect the endpoints of E, there's some edge that's worse than E, has bigger weight. The goal is to get the minimum weight spanning tree. Okay, so here then is a very strong lemma. It's saying that an edge is good if and only if it is in every single minimum weight spanning tree. There may be more than one minimum weight spanning tree. But it's saying that these edges are very safe. If I know that any other path connecting the endpoints of E has a bigger edge than E, then I know that E is in every single minimum weight spanning tree. It's not yet clear how to certify or figure out if an edge is good. We'll do that next. But it does tell us that if I can make an algorithm that only takes good edges, that would be great. That would be fantastic. Okay. All right, so at some level, if we prove this, we're very close to understanding everything. Okay. All right, so let's suppose 1. All right, so let's suppose that every minimum weight spanning tree, every MST is sometimes the acronym, contains this particular edge E. Okay. Now, suppose E is not good. Okay. All right, so what am I going to do? So let's suppose two things. So let me first draw a tree. Okay. And Rex. Okay. And okay, so let's say that this edge is E. Then this is a minimum weight spanning tree that contains E. Okay. Now, okay. Actually, let me set up a little different. Okay. So let's first suppose that if E is not good, then I know that there's some kind of spanning set of edges where all the edges in that spanning set are smaller than the weight of E. By definition of not being good. Okay. Now, together this presents a cycle. Okay, so if E is in a spanning tree, at least one of these edges must be omitted from the spanning tree. So maybe this spanning set looks like this. Okay, let me actually do this again. Maybe the spanning set looks like, okay, so maybe that's the set of edges that proves, that establishes that E is not good. So it's a set of edges that spans E. So it connects the endpoints of E, but the weight of every edge is smaller. Okay. Now, if I look at the tree, where on one hand I first delete E. Okay, that splits my blue tree into two components. Now it's just a forest. Okay. But my red path starts at opposite endpoints of E and connects it. So I know that at some point, if I follow this path, I will have to cross over to one component to the next. There will be some edge that lets me fix the tree, just by virtue of starting one component, it's a path, and it ends up in the other component. So at some point we hop over. Okay? That is some edge F. Okay, and since it's a counterexample to the good thing, I know that the weight of F is less than the weight of E. Okay. But now if I take my original tree, I delete E and I replace it with F, the weight would have gone down. I would get a tree again, but the weight goes down. Okay, but we had assumed that the tree was a minimum weight spanning tree containing E. Okay, so that can't happen. Okay. Okay. Let me look at the. Okay. Let's look at the opposite direction. Okay. So, suppose E is good. But one fails. So there is some minimum weight spanning tree that excludes E by contradiction. Okay. Let's assume contradiction. Okay. So suppose I'm drawing here like a minimum weight spanning tree. Okay. But the claim is that E is good, but the tree is not including E. So maybe here is E or something. Okay. So purple is supposed to represent a minimum weight spanning tree. E is good, but apparently is not in the minimum weight spanning tree. Okay. Now, since E is not in the minimum weight spanning tree, but the tree is spanning, by definition, I know that I can go in the tree from one end to the other. Right? There's some path in the tree. F1, F2, F3. Okay? And I know that E is good. So E has to have weight that's bigger than one of those edges. Okay? So maybe, for example, the weight of F2, E has to have a weight smaller. Maybe the weight of F2 is bigger than the weight of E. E is good, so it's smaller than somebody. Maybe F1 and F2 are, F3 are smaller, but not F2. But if that's the case, then we can delete F2, add Fe, get another spanning tree, except with smaller total weight. So purple was not really a minimum weight spanning tree after all. And so that's our contradiction. Okay, so at some level, if E is good, it's always in every spanning tree. It's pretty strong characterization. Okay, so what that suggests is sort of a very generic algorithm, which at some level is not really a concrete algorithm. But what we've shown is that, okay, we have this characterization of quote-unquote good edges. And I know that good edges are in every spanning tree. So why don't I make an algorithm that just keeps trying to take good edges? I know all of them are safe. Okay. But there's two remaining issues. One is, what if I run out of good edges? Right, it's not obvious that I've taken a few edges. They were all good at the time, so I feel good about it. It's not obvious that there's more good edges left. Maybe there's edges in the minimum spanning tree that aren't good. That could be possible. The other option is, the other issue is I don't know how to figure out if an edge is good. I mean, it seems like a short definition, but at some level I have to check all these sets F. There's so many sets F out there. There's so many maybe ways to connect the endpoints of E. Yeah?
Just like a question, if you found a minimum spanning tree with all good edges, wouldn't that be like the only minimum spanning tree you could find?
That would be great. So if this algorithm terminated, if A, we figured out how to identify good edges, and we can argue that every edge is, it terminated and we're able to find the good edges, yeah. If this actually produced a tree, then actually, A, we know that it's a minimum weight spanning tree, because it's only taking good edges. But we also know that the minimum weight spanning tree is unique, because we filled up a tree with edges that are in all minimum weight spanning trees. But that means there could only be one minimum weight spanning tree. Right? Okay, so that's the overall framework. I'll end up presenting three, more concrete algorithms, but they all kind of fit into this. We're going to understand that they're all always taking good edges and figuring out and identifying good edges in a different way. And we'll conclude, not only can we find a minimum weight spanning tree, but the minimum weight spanning tree is unique. Okay. Ultimately, that does use the fact that the edge weights are distinct. If they weren't distinct, it's not unique, but the same ideas will still extend. Okay. All right, so we need a better definition or a more useful characterization of good edges. Right now we don't know how to find good edges. Okay. So here is this claim. It says, let H be any set of edges that maybe is not spanning the whole graph. Okay, so maybe... Alright, so we just have some edges out there. Okay. And now there might be a lot of edges that aren't spanned by red. Right? So these are all edges where the endpoints are not connected by red. Okay. Now, all these edges have different weights. Okay. And let's let E... why did this stop? Okay. Let's let E, among those edges that aren't spanned by red, let E be the one with minimum weight. Okay. The claim is that E is good. Okay, so any set of spanning edges, any set of edges out there in red, and then I say, okay, those already connect some stuff, but let's look at the edges that aren't already connected by the red. among those which has the minimum weight, then we're going to show that that edge is always good. All right. Okay, so this proof is not so bad. So I want to show that E is good. Right? So let's look at any other set of edges that connects the endpoints of E, which might include some edges from our set H. Right? So that would be a set of edges that spans E. I want to see if E is good, which means I want to show that E has weight smaller than one of the purple edges. Okay. Now, I know that the red by itself does not span E by choice of E, right? So one of those purple edges aren't red. In this picture, many of them are. Okay. But I know that, say this edge here, that purple edge, which is not red, also is not spanned by. Well, let me be more precise. Since E is not spanned by red, one of those purple edges are also not spanned by the red. Okay. So in this picture, this edge F is not already connected by any red edges. Okay. And E was the smallest weight among all of the edges that aren't spanned by red. So in particular, E has weight smaller than that edge F. Okay. Right? If by contradiction all of these edges, all the purple edges were spanned by F, I could have combined sort of all those paths to span E itself. So one of those edges had to be not spanned. Okay, good. So that gives one relatively simple characterization of good edges, which then suggests the following greedy algorithm. Okay. So we'll start with an empty tree. Okay. And I'll sort the edges in increasing order of weight. Okay. And one by one, I'll keep adding the minimum weight edge that doesn't create a forest. Okay? And each edge I add can be understood as the minimum weight edge that's not already spanned by the edges I've taken. Okay? So at every intermediate point of the algorithm, I'm thinking of the set of edges I've taken so far as that set H from the previous lemma. Okay? And I keep adding the minimum weight edge that's not already spanned by my tree or my forest at that point in time. Okay? That edge is automatically good. So I can sort the edges in increasing order and just keep adding them as long as I don't introduce any cycles, because those edges are already spanned. And I will naturally fill out a whole tree. And along the way, I know that every edge is good, so we'll get a minimum weight spanning tree. Okay. All right, that's the first of three algorithms. Okay. Okay, so next one I'll actually need one more lemma that I forgot to write down. Okay, so let me get rid of this. Alright, so that was one algorithm based on this lemma 13.7, based on this set H. Let me give another characterization of good edges. Okay. Let's let S be a subset of vertices. Okay. It's some set of vertices V. And let's let E be the minimum weight edge subject to E being in the cut. So what do I mean by the cut? Let's look at all the edges that have one endpoint in S and one endpoint out of S. Okay? Maybe that's that one there. Okay? The claim is that this edge is good. Okay? And to prove this, I'm just going to use that previous lemma, and all I have to do is find out was a clever choice of H. Okay? What will my choice of H be? I'm going to take all of the edges that are completely inside S. That's one part of H. And I'm going to take all of the edges that are completely outside of S. Okay, that's my set H. Okay. So this graph may likely have only like two components or something if the outside is completely connected. Okay, so the edge is on the outside, the edge is on the inside, and E is sort of the best edge that's going across. So E is not span, right? Because there's no edges going from inside to outside. And E is the best one out of this set. Okay, so the minimum weight edge in every cut is also always good. Okay, just leveraging this previous lemma. Okay. So that gives rise to two algorithms. One is sort of search style, one is sort of like a parallel algorithm. Let me explain the parallel one. Imagine, okay, you start with n vertices, n connected components, all by themselves. And each round, every vertex picks the smallest edge that's incident to it. Okay. So maybe, and it's possible that vertices choose the same edge. Or two vertices choose the same edge. Okay? But each edge is chosen is the smallest edge incident to that vertex, so it's sort of the smallest edge in that cut induced by the vertex. So for each vertex, chooses the smallest incident edge. Okay? And those are good because those are automatically in the spanning tree because they're the smallest edge leading. Here, S is just that vertex. Okay? But now I can repeat, right? I can treat this connected component after one round as a set S and find a minimum weight edge that leaves this set. Okay, so my second round might pick an edge like that. So for each connected component, I'll pick the minimum weight edge leaving that set. Okay? And maybe both of these components choose that one or something. Okay? So each round, I have a forest, and every component chooses the smallest edge incident to it that leaves its own set. And then we add that. Those are always safe. Those are always good by our previous lemma. Okay? The nice thing is that each time sort of the number of connected components goes down by a factor of 2 because everyone gets joined up with some neighbor. So you need log n rounds, and it's not hard to do all this in linear time per round. Okay. The last version looks a little bit like Dijkstra's algorithm, and in fact it uses Fibonacci heaps to make it as fast as possible. Okay. It's sort of similar, but instead of sort of adding a bunch of edges in parallel, we sort of start with one vertex and we gradually grow it out. Okay. So here's some vertices. Okay. And let's say I start here. Okay. I'll treat this as my first set S. and I add whatever's the minimum weight edge leaving that set. I make this my second set S. I add the minimum weight edge leaving that set. Okay. So in this fashion, I gradually grow a tree until it spans the whole graph. But I'm always looking at my component saying, what's the smallest edge that leaves it? And by our analysis, that's always a good edge. Okay. All right, so much for that. So I won't do the running times in too much detail. I'll just roughly explain. Okay. The greedy algorithm, you do need to use this data structure called disjoint union, so that you can quickly say, okay, is this edge already spanned? And at some level, are the endpoints already in the same component? So this is addressed by this disjoint union data structure, which you guys may or may not have seen in your data structures class. You have? Okay. Okay. So this will give you m log n, because you do have to sort the edges at the beginning. The parallel algorithm, each round that's a sign. Okay, so the parallel algorithm, each round you vertices by 2. Each round takes linear time. You need m log n. Okay, but that algorithm actually probably works best in practice. We're back. And lastly, when you did the search algorithm where you're kind of crawling out and you're gradually adding, you need to figure out the next best edge and sort of the next nearest neighbor to add. Okay, but you can do this with a Fibonacci heap, which will very quickly, in the exact same fashion as Dijkstra's algorithm. So you can actually do this a little bit faster, although in practice I think Fibonacci heaps are so complicated that it might lose on a lot of basic data sets. But you can use Fibonacci heaps to figure out very quickly what's the next edge to add, next edge to add, next edge to add, and you only need m plus n log n time. Okay? But at some level, these are all the same algorithm. They're all taking good edges. Okay? All right, that's it. Thank you.